Welcome everyone. This separation processes course. Today our topic is batch distillation. So we are still talking about distillation, which is a method of separating two or more components based on the difference in the boiling point. But now we will talk about batch. What do we mean by batch? Batch means it is not a continuous process, so you have a change with time. It is not continuous, it is not steady state, it is unsteady state behavior. Okay, so you don't have a continuous feed, not like you have that we discussed before when we have this column and continuous feed here, and then we have continuous product. No, batch distillation means it is like you have this, they call it still bot, where you have your mixture here. Let's say it contains A and B. Then, for example, you apply heat, use your heater on high uh, high temperature steam. Then you heat this. Then the production, it is like what we did usually in chemistry lab. Then the product you collect, you have your product here, you collect it. Okay, and if we said and if we said uh, let's say the more volatile component is A, so as you heat, this A will be easily goes to the vapor phase. Then you can add here a cooling system, for example cooling water or whatever, to condense this vapor and collect it here. Okay, so it will mainly contains A and mainly A and some B. Okay, and then after some time, from time 1 to time 2, the end. Okay, after some time you will left with a liquid quantity here that contains mainly B, the heavy component, and whatever you collect here will contains mainly A, so you separate them. You did your separation. Okay, again based on the difference in boiling point, which is the difference in volatility. Okay, so that's batch distillation. In batch distillation uh, we have mainly three modes, famous modes. We have three modes for batch distillation. The first mode is called simple batch distillation. uh, yeah, and the second mode is called batch distillation with rectification. Okay, and this mode you can split it. So this mode, rectification, you can split it into two. We can have rectification at constant reflux ratio, or rectification with constant XD, distillate composition of the more volatile component. We will talk about all of these, but as a general idea, this simple batch distillation, it is like single stage. So you have only this still pot, and that's it. You have this still pot, and then you collect your products here. But if you have a rectification, it means that you have stages. You don't have like one stage here. The one stage is only the still pot where the liquid is vaporizing. Okay, but in rectification you use some equilibrium stages. For example, you attach them here, like this. You have, this is the still pot, this is stage 1, single stage. If you have only this, so this will be simple batch distillation. If you have here some stages, and then you take the product and you do some reflux, then you collect your product here. Then, so this is the reflux, and you have here XD, composition of the distillate that you collect here. Then this is called batch distillation with rectification. So rectification means addition of stages. You add some stages here. Okay, if you add the stages and you use some reflux to maintain the continuous contact between liquid and vapor, This we call batch distillation with rectification, and it has two modes. One mode is to operate at constant R, so you fix this reflex, it, it doesn't change. This reflex is fixed, so XD will be variable, it's changing. As the time proceeds, of course, XD will change. Okay, the distillate. Or you have another mode, usually we do it through controllers. We need to use some controllers, which is not the scope of this course, it's the scope of control process. Yeah, control process course. Use some controllers in order to control this reflex ratio to be constant. This we call constant R. Constant XD, it is somehow more difficult. You need to use some controllers in order to fix this composition, and to do this you need to play with the reflux ratio, so the reflux ratio becomes a variable. So let's discuss them one by one. First we will start with simple batch distillation. But before I discuss the simple batch distillation, I want to mention something. Yeah, I want to mention important something, that describing batch distillation. To describe batch distillation, we have an equation called batch distillation in general, with a simple or rectification. So batch distillation in general, we can use an equation called Rayleigh equation. Rayleigh equation for the scientist Rayleigh, which is a famous scientist, especially in heat transfer. I'm sure that you heard about this name before. The Rayleigh equation. So this is Rayleigh equation. Rayleigh equation is used to describe batch distillation with a simple or rectification batch distillation. This equation tells you that ln of W over W naught is equal to integration from xW naught to xW dxW by yd minus xW. This is a general equation. Okay, and what I want to mention here is every equation has a story, and the story of this equation is, let's discuss it one by one. Suppose we have a time 1, let's say it is 5 p.m. Then after some time we have time 2 after some time, which is, let's say, 6 p.m. in a given day. Okay, so we have here, this is our still bot. Okay, and we have the product here. We collect them into a vessel or a storage tank. Okay, the initial amount of liquid presents here. Initial amount of liquid presents here. The mass of this liquid, or the number of moles, in other words, and you can know the relation between mass and moles, it's just the mole and mass. Anyway, let's say the number of moles of this amount here initially at time 1, and we refer always with time 1 as time 0 if you take this time as your reference, so you refer it to time 0. And then this, after some time, we call it time t. So from time 0 to some time t, okay, which is, for our example, they are 5 p.m. and 6 p.m. So in our example, t is equal to 0, the initial time is 0. After some time, which is 1 hour in this case, we will have, this is the duration of the process. Okay, so the mass of, or the number of moles of the liquid mixture, of course we have here A and B, of this liquid mixture, we call it W naught. So the W naught refers to the number of moles contained initially at time 0. Then after some time, this is your still pot. After some time, of course you are heating here, you use heat. Okay, you are heating, so what's happening is that some amount of this liquid is vaporizing. So as this vaporizes, what will happen to the quantity of the liquid? It will decrease, right? So the quantity or the number of moles of liquid that we left after the end of the process, we call it W. Okay, so this is W and this is W naught. Okay, and then what's this YD and XW? YD is the composition of the distillate and XW is the composition of the waste. Oh, yeah, waste. So initially, يعني what do we mean by XW naught and XW naught refers to initially. So initially the concentration here or the composition is XW naught. For A would be of course for the more volatile component, which is A. For example, in this case, let's say A is the more volatile component, so XW naught is the composition of A in the still pot at time 0. After some time, what will happen to this composition? We are heating, so the vapor will be generated, and as A is more volatile, so more A will be collected, more A will leave this still pot. So of course XW will decrease. So the composition of the A after some time we call it XW, and of course always XW will be less than XW naught because we are vaporizing. Okay, so this is XW and this XW naught. YD is same as XD, which is composition at the distillate. What is the composition of the distillate here, XD or YD? Okay, yeah, that's the Rayleigh equation. So now let's start with the simple batch distillation. Simple batch distillation. The simple batch distillation, in other words, in simple batch distillation, we don't have reflux, we don't have stages, we don't have this complexity. That's why we can say that the distillation the distillate composition is nothing but the composition in the vapor phase, because we have only single stage. And we can say also that composition in the still pot XW is just the composition in the liquid, because we have one stage. We don't have that too much stages, and each stage we have its own X and W, X and W. No, it's just a single stage. That's why we can use this, and then see this Rayleigh equation. We replace XW naught with X naught. We replace XW with X, and we replace the XW with X, YD with Y, XW with X. So we will left with this equation. This equation is only valid for, that I'm going to write now, this equation is only valid for simple batch distillation, which is then W over W naught is equal to integration from X naught, the initial composition in the liquid phase, up to X, the final composition in the liquid phase, dx over 1 y minus x. Yeah, that's it. This is the equation derived from where? From the Rayleigh equation. And the Rayleigh equation is derived from where? It is derived from a simple material balance using unsteady state process material balance, mole balance around the still pot. Okay, so that's it. This is the equation for the batch distillation. Now, the problem here is how to find, for example, if you are interested to know, the quantity that we left with, which is W, after some time, if we know the initial quantity W naught, the problem here is how to calculate this integration. We can have three ways. The first way is if we have a table that contains X and Y values, the equilibrium data. Then what we do? We use numerical integration. So how to integrate this? Integration of dx y minus x. We have integration of 1 over y minus x. Integration of y minus x dx. So what's our f of x here? What's our f of x? This is f of x. This is our f of x. Right? So this is our f of x. So in order to integrate, what we will do a table, same as numerical table, to do numerical integration. Then the first thing is to have this x starting from x naught till the end. okay, the initial composition of the liquid phase. Of course, we refer to composition as always to the more volatile component, okay. Then we have these values of y, starting from y naught till the end. Then what we will do, we just find f of x, as simple as this. F of x will be 1 over y minus x. You find 1 over y minus x for this, then for all values. Then you do numerical integration. One of the ways is to use trapezoidal rule. So if you want to find integration, this one, only this part. In other words, we can say ln w over w naught equal to I integration. How to find this integration? One of the easiest ways to apply a trapezoidal rule, or you can use Simpson 1 by 3 rule, Simpson 3 by 8 rule, quadrature rule, or whatever numerical method, but the easiest way is the trapezoidal rule, yet enough for design calculation. And this integration is just, they find it as h over 2, if I'm not mistaken. Then you find f naught plus 2f1 plus etc. plus 2f n minus 1 plus fn. So it is like if you have, for example, 5 points. If you have 5 points, then it will be f1 plus 2f2 plus 2f1 plus 2f3 plus 2f4 plus f5. So in between, you multiply each f by 2 at the beginning, and at the end, you don't have to do this. Okay, this trapezoidal rule. So that's why we make this table in order to find f of x at different points. Then we use this rule. And what's this h? H is just p minus a over n. Okay, so if n is the number of intervals, be careful here. N is number of intervals. It's not the number of points. It is like if you have 5 points, like here, 1, 2, 3, 4, 5, 6, 7. Let's say 7 points. How many intervals we have? They will be number of points minus 1. How? Because from here to here is 1 interval. 2, 3, 4, 5, 6. 6 intervals. So this n is not number of points, it's number of intervals, which is number of points minus 1. Okay, and what's this p and a? P is the final composition in the liquid phase. A is the initial composition in the liquid phase divided by n. Okay, so the final value of x minus the initial value divided by the number of intervals, you can get this h. Then you can get this integration, and of course we are not interested only in the integration. At the end of the day, we want to find w, right? The quantity of the liquid that we left with. So we can say ln w over w naught is equal to this integration, or in other words, w is equal to w naught e to the power integration. If you have integration, you know your initial quantity, you can get w easily. Okay, that's it. And we have some special cases, like special cases of this equation. The first special case is if you have a constant k distribution coefficient, and you know this distribution coefficient is y by x, distribution coefficient. If you have this constant, then you can use analytical integration. You will substitute with y is equal to kx. Okay, then you can integrate the equation analytically. You don't have to use a numerical integration. Then you will left with this equation. Then w over w naught is equal to 1 over k minus 1, the distribution coefficient. Then x over x naught. You can try this integration. It is just the integration of the Rayleigh equation, substituting y with kx. Okay. The third special case is what if you have a constant relative volatility alpha. If you have a constant relative volatility and this assumption looks valid, then what you have to do is you again integrate the equation analytically. It's somehow difficult to integrate, but if you have time and you try this integration, you will left with this analytical integration. Then w naught over w equal to 1 over alpha minus 1. Then we have ln x naught over x plus alpha ln 1 minus x over 1 minus x naught. Yeah, that's it. This is the analytical equation, and you be careful that it's only valid if you have a constant relative volatility. If you have a constant distribution coefficient, you can use this equation. If you have a table, you don't have constant alpha or constant k, you have a table, then you need to go for trapezoidal rule and integrate this equation analytically, numerically, numerical integration, trapezoidal rule or whatever rule. Okay, and there's an good equations to discuss using material balance. You have this, right? You have this your still pot, and then you collect the sample here, you collect your product here. Okay, so let's do a material balance. If you do material balance around this still pot, so you can see that the initial quantity W naught, initial quantity here, is equal to, after some time you will left with some quantity W, صح? And of course this W is less than W naught because you are vaporizing. Okay, so of course this W naught will be summation of the left quantity after vaporization, after the process finished, plus something called D total. What do you mean by D total? D total is the total amount that you collect here, which is a logical equation. Logical equation. Yeah, if you start with a specific quantity W naught, after some time you will get some quantity left here and some quantity collected here. We call this D total, the total quantity collected. So it is not a rate, it is not like mole per time second. No, 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 it is just quantity, mole. Because we are dealing with batch, not continuous. Okay? So this is it. Also, this is for the overall. If you do overall material balance, if you do component material balance, it is like you multiply by the composition each side. So you will get this equation. You have this, you know this equation, right? W naught plus D total. Now let's multiply by, so in other words, we are doing material balance for components. So it will be XW naught, XW, then XD. But the problem here, a very important problem that I would like to discuss is that there's a problem here, is that this XD, it varies with time. As you vaporize, you will take more B with you, isn't it? And B is a heavy, but as you vaporize, you are giving more heat, so you are initiating this heavy component to be also vaporized. So what will happen to this XD, which is the composition of A, it will decrease. Okay, so you don't have this constant XD in simple batch distillation. That's why we feel the need to use the average value. And the average value, how to measure it? Simply, you take a sample here, from this product, you analyze it in the lab and get XD average, which is the average distillate composition of the more volatile component. That's why we use average. Okay, that's it. Yeah. Okay. Suppose if we are interested to calculate the time of distillation, how much time we need to wait in order to get this degree of separation for distillation. So it simply can be calculated through using this equation. Time is D total, the total quantity that we collect, over the D. D refers to the rate. The rate. Why? Because you know we have this still bot. It is like, I like to say that it is not batch, it is semi-batch. Why? Because you don't have continuous inlet, but you have a continuous outlet, and then you collect this outlet here. The amount that you collect here, we refer it to D total, total amount. But as the time proceeds, there is some rate here, some continuous product. It is like semi-batch process, but it is under the umbrella of batch distillation. Okay. Anyway, for this rate here, the flow rate of vapor leaving the still pot, we call it D. D total refers the total quantity that you collected at the end of the day. If you divide them, of course, this has a unit of mole or kilomole. This has a unit of mole per time, let's say mole per second. If you divide them, you get unit of time. This is the time required for distillation. Okay, this is the time required for distillation. And by the way, this equation is not only valid for this equation, only this equation is not valid only for simple distillation. It can be used also in batch distillation with rectification, but be sure that this d is constant. If this d is varying, if it is not constant, then you cannot use this equation. And we will see we are going to use another equation if we have a constant, if we don't have constant distillate rate. We need somehow integration to get the time. Okay, and you can know this equation can be written in this form: W naught minus W over D. From where we get this? Because we know from material balance D total is W naught minus W here, right? We discuss it. This one, W naught is equal to W plus D total, so D total is W naught minus W. So you can get this final equation that you can use in order to get the time for any batch distillation with a simple batch or batch with rectification. Okay, but provided that this D is constant. Okay, what else? Okay, and already we discussed this equation, right? This equation we discussed it. Suppose if you are interested to calculate rather than going to the lab and take a sample and measure XD average using an analytical chemistry technique like spectroscopy or whatever technique you use, instead of doing all of this, can we calculate this XD average? Yeah, we can. If we rearrange this equation in terms of XD average, just try to rearrange this equation, you will get this equation: XD average. This is if you are interested to calculate the average composition of the distillate and the product that we collect. If you rearrange it, you will get it as this: XW naught minus W naught minus XW multiplied by W over W naught minus W. That's it. This is if you want to get this XD average. Okay, regarding there's a point that I would like to mention. It's regarding numerical integration. A problem that we face in numerical integration is that we don't have an equal intervals. يعني if you have this x and w, if you have here 0.5, then 0.4, then 0.3, then 0.2, then you can see here somehow we have a constant interval which is plus, not plus, minus 0.1. This is our h interval. We move minus 0.1, 0.5 minus 0.1, 0.4, then 0.3, 0.2. Then in this case we can use the trapezoidal law that we already discussed, which is h over 2 f naught plus 2 f1 etc. up to fn. We have already discussed this. Okay, but the problem here, what if we have unequal intervals? What if we have unequal intervals? We have, for example, something like this: x and y, then we have 0.5, then 0.45, then 0.31, etc. whatever. So you can see we don't have a constant interval. So this case we call it unequal intervals. And is there a solution for this case? Yes, there is. We can apply again a modified form of trapezoidal rule that's in this form: I, the integration, is equal to summation of xi minus xi minus 1 multiplied by f of x I minus 1 plus f of xi divided by 2. What we are doing here, suppose we have only 3 points, then what we will do, we will say this will be xi here will be 0.45, xi minus 1 will be 0.5, f of xi minus 1 will be the value of f. Remember, when we calculate f of x, the value of f at xi minus 1, and at this point, this will be f of xi minus 1. Then f of xi will be the value of f of x at this point. Okay, then it is summation. So you need to continue, then plus, you take a plus, then continue. This will, let me do it in a different color. This will be your xi. This will be now your xi minus 1. This will be here your xi, f of xi, and this will be here your f of xi minus 1. Then you continue until the end of all points. This is your integration. You can use this equation if you have unequal intervals. It's just a numerical equation. Okay. Now, so that's all for the simple batch distillation. Now let's discuss the rectification, and we are going to discuss only the binary mixture. I want to start with simple things. So we'll discuss binary batch rectification. Binary means we have only A and B. Suppose in the A it is the more volatile and B is the heavy component. Again, as we said, we have two modes of binary batch with this rectification. The first mode is constant R, the second mode is constant D or constant XD. So let's start with, and as we mentioned, it is easier to work with constant R from the control process point of view than working with constant XD. So let's start with the easiest one, which is constant R. What we have to do here for constant R batch rectification, so we will start with constant R. This is for constant R. This is for constant R. And we are going to do some assumption here that we have a constant boil up. What do you mean by boil up? Again, you have here, this is your still pot, but now it is rectified. Rectified means we have here some stages. Then you take this, so in order to maintain a constant contact between liquid and vapor in these stages, you need to draw some reflux back, and then you take your product. So this will be your product, you collect it in a tank or whatever. Okay, so we are going to assume that this vapor leaving the system, let's call it V, which they call that boil up. We are going to assume it constant. And you know that R is constant for this type, and R is just L over D, right? This D distillate, and this is the L, the liquid, returning to the still pot. So if you have a, and you know that from material balance that V is equal to D plus L. So what I want to say here is, if you have constant V and you have constant R, in other words, you have constant L over D. So L will be R multiplied by D. So this R by D will be constant. So you will have also constant L. So for sure you will have constant D. So everything here is constant. In this case, you can find the time needed for distillation, as we mentioned, using this equation. Time will be W naught minus W over D. Then we can play with this equation. We can say W minus W naught minus W, and this D for material balance is V minus L, right? If we rearrange this equation, it will be V minus L. Okay, and you can further play with this equation by defining the reflux ratio. You know, reflux ratio is L over D. Okay, reflux ratio is L over D. Okay, so for example, you can divide both sides by D or manipulate this equation somehow. At the end of the day, you will reach this equation, which is T is equal R plus 1 over V W naught minus W. So this equation can be used if you have a constant R batch distillation in order to calculate the time. Now, what if we are interested to calculate the W, the quantity that we left with in the still pot after the distillation? Again, we need to go back and use Rayleigh equation. This equation, if you remember, this Rayleigh equation. Yeah, I think, let me write it again. Yeah, we need the Rayleigh equation, which is ln W over W naught is equal to integration from XW naught to XW dxw over yd minus xw. You need to so again, let us call this one, let us call it I. Okay, so again w will be w naught e to the power I. The problem here is how to calculate this I. So if we know this I, we can use this equation directly to get w, right? So this is again an integration. Again, we are going to use we are going to use we are going to use numerical integration in order to integrate this. And how we are going to do this? We need first thing is to plot. We need to plot like this. See, you need to have your, suppose this is your graph paper, this is your graph paper, okay, and this is your x and this is your y, liquid and vapor compositions, uh, and this is your 45-degree line, and let's say this is your equilibrium curve. Okay, again this is constant r, and when you say constant r, this means constant slope. Slope will not change, and xd will change. So you can start at time 0. This will be your xd, which is xd naught at time 0. Okay, then using the constant reflux that you know, you can calculate the slope, right? You can calculate the slope, and from a slope and the point you can draw a curve. Okay, so you can draw a curve like this. Okay, and suppose, let's say we have two stages. Let's say we have two stages, for example. Then what you will do, you will start from, as makeup delay method, you start from xd naught, then you go 1, 2, so this will be your xw naught at time 0 at xd naught. Okay, then we need to move this line again and again. We move this line, it is constant r, so the same slope, so all lines will be parallel. We need to move this line, but the question here, where to stop? Until where we stop moving this line? We stop until a point, we stop until the point that if you draw this number of stages, you will end up with xw, the final, after some time, the final composition of the more volatile component in the still pot. So it is like you will stop here where you draw these two stages, then the value here will be xw. Okay, so the first step is to draw this line that starts at xd naught, okay, and xw naught. Then you draw this line, that's this line, if you draw it and draw the stages, you will end up at xw, which again refers to xd. Then in between, we just draw some random line. For example, let's say 3 lines, 1, 2, 3. You draw this random lines. Okay, why we are doing these random lines? Because we will need them in integration. So you draw this random line, then you start counting 2 stages, then you read xw. So it gets crowded here. Let me write it in simplified way. So what will happen is that you will get different values of you will get different values of xd and different values of xw. So let's say you get, starting from, you get xw naught from curve 1, then xw1 from curve 2, then xw2 from curve 3, xw4 3 from curve 4, all the way to xw, which is the final composition, and at each xw you get the corresponding xd naught, then xd1, then xd2, then xd3, then xd, the final composition. Okay, so these all you can read from the figure using the given number of stages. Okay, then what you will do is that you will go and, of course, xd is same as yd. We are assuming a total condenser. Okay, so xd same as yd. So what you will do, you will draw a table to integrate numerically. Then this table, you will start with xw, starting from xw naught you all the way until xw. Okay, then you write the corresponding xd or yd values, they are the same, that you again get it from the figure xd naught all the way until xd. Then what do you want to integrate? You want to integrate 1 over yd minus xw. Okay, then what you will do, you will find f of x, which is 1 over xd minus xw. So you will find these values. Then you see, in most cases you will have unequal intervals. So what you need to use, you need to use trapezoidal rule based on unequal intervals. This trapezoidal rule based on unequal intervals in order to integrate. Then once you integrate, you can get the integral. From the integral, you can get, from the integral exponential of the integral w naught, you can get your w. So that's it. This is for the batch rectification with constant r. The last thing here is, what if we have a constant xd? Batch rectification with constant xd. Since this xd is constant, we can do a very good assumption that is highly valid, that we can see the instantaneous composition of D is equal to the average composition that we are going to collect at the end of the day, because xd is constant, it will not change. So this is a very good assumption that we can do in order to solve this type of problems. But again, the problem here is that again, we are going to assume constant boil up, constant V. But the problem here, we have this reflux ratio, it is not constant, and you know that this R is L over D, so this one is not constant. So L over D, or L and D, each one of the L of D will be variables, will be not constant. In other words, D is not constant. So you cannot use, D is not constant, so you cannot use this equation, W naught minus W over D. No, because D is not constant. What we need to use, we need to apply an equation to calculate the time. We need to apply an equation rather than this equation that helps us to calculate the required time. And this okay, so since, as we said, D is not constant, it is not constant, so we need another equation to calculate the time. We can calculate the time through this integral equation, where we have W naught xd minus xw naught over the integration from xw to to xw naught. It's a reversed integration from n to beginning, dxw 1 minus L over V xd minus xw whole square. So let's go over this equation term by term. What's this? W naught is the initial quantity of liquid in the still pot. What is this xd? It's constant, because it's constant xd. Then it will be the constant distillate composition that we have. Xw naught is the composition of the more volatile component in the still pot initially. V is the vapor boil up rate. Okay, and xw is the final composition in the still pot of the more volatile component. Xw naught, as we said, is the composition of the more volatile component in the still pot. Then we have, this is our integration. We are integrating this function with respect to xw. So this is our f of x that we are going to integrate. So again, we can call this part as a whole. We can call this part as I, as we said before. Then if we find I, we can multiply it by this term to get the time. Okay. Uh, so in this I, you can see the first thing that we have here, we have L over V. What's this L over V? It is like makeup today. What's this L over V? It is the slope. It is the slope, so you can calculate it from the slope of the line. Okay, and again, xd is constant, which is the composition and the distillate of the more volatile component, and xw is a variable because you are integrating with respect to xw, dxw. So this xw will be variable. The question here is how to determine this slope and xw, then you can integrate it. So you need to make a kind of table. You need to make a kind of table like this to numerically integrate this integral. We want to find I, this integral, to get the time. So we can make a table like you start with your independent variable, which is in this case your independent variable xw. Then you give the slope L over V. Then you find f of x. Okay, and what's this f? This function that you have, that you are integrating, is 1 minus L over V multiplied by xd minus xw whole squared. Okay, so you will start the values of xw starting from xw up to xw naught. You will have different values. Then but the question here, how to get this xw and the slope? Again, you need to draw using makeup delay. So suppose this is your graph paper. This is your graph paper, and this is your 45-degree line, and this is your equilibrium curve. So what you will do, you will specify where is your xd. So this is x and this is y. Here, for example, here is your xd. Your xd, and it's constant. And we have variable r. This r is variable, right? And we are in the case of the constant xd. So variable r. So the slope will be variable. This slope will be variable. Okay. So you need to start with a line that, suppose again we have two stages, or whatever stages you have. Suppose we have two. So you need to start with an initial slope that if you draw this slope, then you count the stages as 2, then you will end up with xw naught initially. Then you need to draw another curve. You need to play with the slope, and play with the slope of the curve starting from xd until you draw a slope that is, if you start here and you count the stages, 2 stages, you will end up with xw. You need to satisfy this criteria. Okay, then once you have these 2 lines, you can take, for example, 2 lines in between, or 4 lines. As more lines you take, the more accurate answer you get, and that is the numerical integration. Okay, more points, better answer. Okay, then for each line again you will do the same story. For each line you do the same story. You count the number of stages. You see, you read xw for each line. As a summary, for each line you will have different slope, of course, and you will have different xw. Okay, for each line. So you will take these values of xw and the slope, you put them here. These are different values of xw, starting from xw to xw naught. Why? Because the integration is from xw to xw naught. Okay, that's why we start from xw all the way to xw naught. Then you plug the values of the slope that you have. The slope is L over V, as we agreed before. Then you calculate this f of x, knowing the slope and xw, and you have already constant xd. You can get different values of f of x, and again it is very difficult to have equal intervals here. It is very difficult. That's why usually you need to use the trapezoidal rule based on unequal intervals to integrate it numerically. As we discussed, the trapezoidal rule, it's just summation of xi minus xi minus 1 multiplied by f of xi minus 1 plus f of xi multiply over 2. So it is like this one is the average value of the function multiplied by the interval. Then you take the summation for all points. That's it. You can take the integral. From the integral you can get what? You can get the time required. Okay. Now what about w? If you are interested to get the final amount that you left in the still pot after distillation finishes. Okay, so how to get this? The easiest way is to apply the equation that we derived before for the material balance, which is this equation. This is the easiest way. No need to use the Rayleigh equation and waste your time and integrate, and you will get the same answer, of course, or somehow close answer. But the easiest way is to apply this equation. You need to apply this equation. We know the material balance equation around the still pot. So we derived these two equations, if you remember. This first equation and the second equation is w naught is equal to w plus d total, or if you rearrange it, you will get d total is equal to w naught minus w. Okay, so we can remove this d total here from this equation, and then instead of it you can write what? You can write w naught minus w. Okay, then you will see what's the only unknown here. We know xw, our final composition that we want to achieve in the still pot for more volatile component. We know w naught, our initial quantity that we started with. We know again this xw, the w that we are interested to calculate, the final quantity, xd average, which is same as xd because it is constant xd, and w naught we know it. So the only unknown here is what? Is w. So you can use the solver to get this w. Once you get this w, that's it. You can use the solver to get this w. This is the final quantity that you left with. So in summary, to summarize what we did, batch distillation can be done through 3 different ways. The first way is the simple batch distillation with no stages, no reflux. The second way is using a batch distillation with rectification, where you use stages and you use a reflux to maintain constant contact between the liquid and gas phases and the stages. And this can be done in 2 ways. The first way is to maintain a constant reflux ratio, and this is the easier way. Of course, as you maintain this constant reflux ratio, consequently you will have a constant xt. You will have a variable xd. Variable xd. The other way around is to play with the reflux ratio in order to maintain a constant xd, which is somehow more difficult. Okay, so that's it. That's all for the batch distillation. I hope you found this video is useful to explain this, and thank you for your listening. I wish you all the best.